and begin. This screencast will cover the remainder of the notes on section 1.2. In this example, it asks us to calculate the maximum possible length for a drinking straw. It's important to understand that your drink does not travel up the straw because of your action, sort of. When you drink a straw, you do so by expanding your lungs and creating an underpressure. This is actually the atmospheric pressure that pushes the drink up the straw. It does this because of the pressure difference between the atmospheric pressure and the pressure inside of your mouth. The maximum height to which a pressure difference can push a liquid is directly proportional to the pressure difference that your mouth and lungs can generate. We can rearrange the equation for pressure at a depth in a liquid to solve for the maximum possible height to which a pressure difference can lift a liquid. If you assume that a person could maybe generate a near perfect vacuum in their mouth and lungs, then it could cause an underpressure of 1 atmosphere. We can insert the values for the pressure difference of 1 atmosphere converted to pascals, the density of water, and gravitational acceleration, and calculate that the maximum possible length for a drinking straw is 10.3 meters. You should note that this length is actually the vertical length of a drinking straw. You could potentially make a much longer straw if you held it horizontally. Part B is really just a plug and chug problem. If you substitute the values for density of water, gravitational acceleration, and the height of the drinking straw converted into meters, then you can calculate that the pressure difference between the atmosphere and the inside of your mouth is 980 pascals. I wrote this number as a negative value because this is an underpressure, 980 pascals less than atmospheric pressure. You can then divide this by 101,000 pascals, and that converts it from pascals to atmospheres for an underpressure of negative 0.0097 atmospheres. If you were to change the pressure inside of an enclosed fluid, Pascal's principle states that the change in the pressure is then transmitted to all other points in the fluid. An example of this is when you press on a squeeze bottle. That increase in pressure from you squeezing on the bottle is transmitted to the entire fluid, which is what forces the fluid out of the bottle. For example, in a ketchup bottle. A very common application of Pascal's principle is the hydraulic lever. In a hydraulic lever, an input force is applied to a small area, which increases the pressure in the connected fluid. This increased pressure can then be used to press a larger piston with a multiplied force because the force is directly proportional to the area for the same pressure. We can use Pascal's principle to determine the mechanical advantage of a hydraulic lever. Increasing the pressure over piston number 1 is then equal to the increase in pressure on piston number 2. If we substitute the force divided by area to either side of the equation, we can then rearrange the equation to solve for the force on piston 2. Hopefully you notice that on the right hand of the side of this equation, force 1 is multiplied by the ratio of areas of the pistons. Mechanical advantage is the factor by which we multiply a force, so the mechanical advantage of a hydraulic lever is equivalent to the ratio of areas of its pistons. For example, a ratio of 2 would multiply the input force by a factor of 2. Hopefully you remember that machines, like a hydraulic lever, function on the principle that machines really just trade force for distance. They don't give you free energy. As far as we know, there's no way to get free energy due to the conservation of mechanical energy. The volume that gets displaced by piston number 1 has to equal the volume of fluid that is displaced by piston number 2, because the total volume of the enclosed fluid has to be constant. You can rearrange this equation to solve for the distance that piston 2 moves. It's the ratio of areas times the distance moved by piston number 1. We can calculate the work done by piston number 2. You could call this the output work. You should remember that work is force times distance. We can substitute the expression that we got on the left column for F2, and we can substitute the expression that we just got for distance 2, and you should notice that area 1 and area 2 are going to cancel out, giving us force 1 times distance 1. So this equation is saying that the work is force 2 times distance 2 is also force 1 times distance 1. The force in equals the force out. So the energy that we put in is the energy we put out, assuming no loss of energy due to friction. In this example, we're asked to calculate the force generated by a hydraulic press. We're given the diameters of the small and large pistons, and we should note that the area of a circle is pi divided by 4 over the diameter squared. So that's going to tell us that the area is proportional to the diameter squared. According to Pascal's principle, the increase in pressure on piston 1 will equal the increase in pressure by piston number 2. So we can use the equation for pressure to show that force is proportional to area, and area is proportional to diameter squared. We can use that to set up a scaling equation that shows the ratio of forces is equal to the ratio of diameters squared. We can then substitute the values for the diameters and solve for this ratio as 1 over 16. We can use this fact to calculate the force on piston number 2, given the force from piston number 1. I'm sorry, I mixed those up. We knew the piston force on piston 2, so we can use that to find the force on piston 1 as 2 kilonewtons. Part B states that the piston moves through a distance of 80 centimeters, the small piston, and it asks us to determine the distance that the large piston moves. If we assume that there's no energy loss due to friction, the work out will be equivalent to the work in. Because work is force times distance and the work is constant, that's going to imply that force is inversely proportional to distance. We can use this relationship to set up a scaling equation. The ratio of forces is going to equal the inverse ratio of distance, which is that ratio of 1 to 16. So the large piston will move 1/16 the distance that the small piston moves, or in this case, 1/16 of 80 centimeters, or 5 centimeters.